So last time we had gone over the beginning of chapter 9, which is really the introduction to, part 2 of the book, where we have these approximate solution methods that are distinct from the tabular methods in the previous section, because now we have, for most of these methods, some vector of parameters, which is some fixed size d, and with the combination of some, function approximator, we're going to use these parameters to estimate the state values in the problem. Whereas before we could have a distinct estimate for every state. Here we're assuming that the number of states, the state space is quite large, and it's too large to estimate without some sort of generalization of this. So here we're sort of compressing the state space to some size d in order to make the problem, tractable, where it would be, intractable if the state space is too large. So in this problem setup, function approximation, in order to actually solve the problem, we have to define this objective that we care about. And the reason why we have to define an objective is because we can no longer just optimize the value of each state. These function approximations are going to, conflate values between states. So we end up losing a guarantee that we had in the previous section where we could just improve our value estimate by ensuring that we can move each state closer to its correct value. Now here, the reason why we define this is because now there's this distribution over visited states, and we need this distribution in order to have this weighted error estimate where we're using the squared error, but in general, like, this distribution will change with the policy, and we have to sort of define, which states that we care about getting a good approximation for. And in this case, the states we care about are the ones that are going to be visited the most frequently under the policy. So the other, reason we need this is because in general, it's impossible for this error to actually be zero. Whereas in the tabular case, we were just trying to move all the value estimates to their correct value. And when the process converged, we would have zero error. Here, we're not going to, it's impossible to have zero error even after collecting an infinite number of samples. And we'll see that depending on the type of function approximation that we're using. But the basic, reason why we can't have perfect estimates is this reason here, is that we're picking a dimension of parameter size for the weight vector, which is, by definition going to be smaller than the state space. So we have to sort of, we have to compress the information about the states. So then all of the methods in this chapter are going to be these gradient methods, because to minimize this objective, we're going to do what's commonly done when you try to minimize, functions like this, where we can actually take derivatives of whatever the function approximator is with respect to the parameters. And if we can take these derivatives, then we can do gradient steps. And in this case, what this is showing is the gradient update rule, where here we have, some true value for the state. And this, v hat represents the value estimate, which is using whatever the parameter vector is at the current time. And this squared here, this difference in the square is that's because we're using here the value error objective, which is the squared error. And then, if you actually use the chain rule on this expression here, like, the reason for the 1/2 here is just so that this step size in this part of the equation, we get rid of the 1/2 factor when the 2 comes down from the derivative. And then the thing that we really need to evaluate here is the gradient of the value function approximation, where here the gradient we're talking about is the gradient with respect to each of the parameters. So, right, this is all the W's here. These are, from 1 to D. There are D parameters. And as these parameters get updated, the idea is that the value function is updated so that, this prediction objective error is minimized. Now, what isn't really clear here is what this, here I've written like V pi, or here, we have some policy that we're trying to calculate the values for the policy. And here, the error term is using, the actual value, which of course we don't have, because if we had this value for each state in the policy, we wouldn't have to do any learning to begin with, because we'd have the answer. So for like all the previous methods in the book, we can replace this with some estimate of this, where, ideally, like we want to use some unbiased estimate for the value at this state. And in the case of Monte Carlo methods, which I don't know if it makes it here. So this is, the stochastic gradient descent. So, in the case of Monte Carlo methods, we just use G for this unbiased estimate, where G is actually the, discounted future return that we can compute for a given episode. But, this method requires that we can generate an episode until termination. So then we can compute G like we normally would by just looking forward at all the future rewards and summing them with the discount rate. But, there was another, so, if we take that, then you can see that this update step in the Monte Carlo algorithm is just replacing this V pi with G. And then it's very straightforward. Everything after that it is the same. And this method works fine because like this G also doesn't depend on the parameters W. So all the steps we had taken previously of taking this gradient and using the chain rule works fine. The other option we had talked about was using bootstrapping instead of the Monte Carlo method. And with bootstrapping, the estimate that we use is actually making use of the current value function with the current set of parameters. So here, like, we have to sample the reward for the next step, but then we have to then compute the value estimate at the transition state in order to use this. So this function is going to replace all of the discounted future returns that appear when we do the Monte Carlo method with a full episode. So, this method is fine, except for the fact that this step we took here, where we replaced this gradient and used the chain rule here, this step assumes that whatever we're using for V pi, that, this gradient is only using the V hat in the gradient. So this is assuming that this piece of the expression doesn't depend on W, which in this case, if we use bootstrapping, now it does depend on W. So later, anything where we're attempting to use this target value is no longer a true gradient method. It's called a semi-gradient method. And it turns out that in the linear case, where this V hat is a linear function, it does converge. Like this method converges. It doesn't actually converge to the same thing that we would want it to converge, but at least it converges. Once you get rid of linear function approximation, it's much harder to prove that this process even converges to begin with, but you can end up trying it and see what happens. But it makes the analysis of the Monte Carlo case is a lot more straightforward because we have this true gradient method and we haven't, screwed up any of the assumptions from the derivation. So I will also point out that while, in the book, they, and in this pseudocode, they have this gradient of the value function, which, of course, if you use the squared error and you use the chain rule, then you end up with this expression for updating the parameters. But, in the future, it's possible where we could actually use possibly a different error function than this. And also, here, like we have the target value and the value of the function approximation, and we have this gradient here. And we could like compute these things separately. Like we could compute this gradient and then compute this delta term and multiply this out. But really, this whole update step could, like this whole expression could be calculated like together. It doesn't necessarily have to be separated between the gradient of the value function and then this delta term. And, if you look at the original expression here, it's really like this is the thing we need to calculate. We need to calculate the gradient of the error term, not just the gradient of v hat. And in the case of most of these examples, the error term is this, or like the error function is just the squared error, and then it ends up, simplifying to this. But depending on what v hat is, this whole thing could be calculated in a faster, like a more straightforward way than this. Like there's cases where we don't even need to construct like the full gradient to figure out how to update the parameters. We'll see that later in some of the examples. But the way I've written this code here is that instead of writing it in this form, the thing that you have to actually provide to do the update is just this update parameters function. And like this function will end up performing this step here. And the information it needs to perform this update is the current state, the target value, which in the Monte Carlo case is just G, and the step size. And of course, like, whatever v hat is will be built into whatever the update parameters function is. But really, like the new information that's going to be changing at every step is the state, the parameter vector, and the target value. Right. So if you look at this, like this pseudocode here, where we generate an episode and do this here for the gradient update. I mean, all the sort of interesting importance to how the update occurs is sort of hidden in this function. But in order to do the gradient approximation, you have the problem. So you have to be able to generate an episode. And here, this is all like using code from previous sections. But this run episode function will just take the problem, whatever it is, and it will produce, a list of states and the rewards that were visited during the episode. And then, those states will then be fed in, and this, will iterate through the episode. It will update G, which is the target value, and then it will do the parameter update. And this is also written such that, well, these are the only like things that are necessary for the parameter update. There could be other arguments that are useful for doing this computation, like a very common like additional argument that would be needed is some sort of vector that is the state representation. So like these states could be anything. They're not required to be any particular type. Because we're not like in the tabular case, we just, like the states are going to be represented by something, but usually to perform these gradient updates, we need to convert the state into some sort of vector representation that then can be used for other processing. So sometimes the v hat, whatever form it is, would require, an additional like vector placeholder that could be used as part of the parameter update. But we'll see that later. In the very simplest case, you don't even need that, and that simplest case will be the first one looked at. The semi-gradient algorithm, it looks very similar here, and here they've done it also like episodically, but it turns out, for the semi-gradient update, like for the Monte Carlo update, since the target value is G, we actually need, in order to compute G, we need the full episode. For the semi-gradient method, we don't need G, we need R, and we need the transition state. And that doesn't actually require the episode to terminate. So this, even though here it's written as like loop for each episode, this estimation method does not require the problem to be episodic. It could never terminate, which is why, well, I've written it here. There's some max number of steps as an additional option. So either, the process will terminate when the max episodes are reached or the max steps are reached. But actually, and then, you have to add this little additional statement where if the episode terminates, we have to reinitialize the state value so that we can sort of start a new episode. But otherwise, we can just, run this on a step-by-step basis. And this parameter update can occur after each individual step. Because again, just like before in the Monte Carlo method, when we do the parameter update, we're passing G in as the target value. And in the semi-gradient method, we're passing V hat in, where here the V hat is computed, using the value estimate at the transition state. So that's why, this is a bootstrap method, whereas the other method is not. So the first, here, I'll sort of explain this chart here, but the chapter introduces the very, the most basic way that you could form an approximation function. And that is state aggregation. So in the case of state aggregation, we need a function that will map a state into a group. And there'll be some fixed number of groups. So here, actually, did they introduce this random walk example earlier? Yeah, so here so I had introduced this random walk example as well. This random walk is similar to the tabular case, except there's this difference where, so the way this works is that there's no actions. This is a Markov reward process, not a decision process, because there are just states and there's some transition function. So what this represents is the random walk has 1,000 states from 1 to 1,000, and whatever state you're in, the transition will occur either to the 500 states to the right or to the left of the state you're in. So these bars are sort of showing the probabilities of ending up in all the transition states from being in this state. So here it's like, as I move this around, this is going to show like the state transitions moving. And the only sort of complicated part of this is when we get close to the edge. So normally you have the full range of states to the right and left. But as this moves closer to the edge, all the probability that would sort of overflow past the edge is considered the probability of terminating and on that side. So here you get more of the probability terminating, and if you go to the extreme case of being in state 1, here these probabilities are all very small, and a full half of the probability is to terminate to the left, and the same sort of thing on the far right, where half the probability is terminating to the right. And for this process, all these transitions have a reward of 0, except terminating to the right gives you a reward of 1. Terminating to the left gives a reward of -1. So it has these symmetrical rewards, and the goal is to compute the value of all the states. Oh, is there a question? Okay, so yeah, this function here creates this problem in this format. Here, since we're using this as an example throughout the chapter, it's useful to have whatever the true values are. Because there's only 1,000 states, this problem can be solved actually with all the techniques from the first part of the book, where we enumerate all the states. So I have a version of this problem where it's actually constructing the problem as a tabular problem here, where this is like all from part 1, where we have all the states listed, and we have the full transition function that describes all of the dynamics of the problem. The only purpose of defining this is so that we can solve the problem completely, and that way we can compare all the approximation techniques to what the true answer should be. So the idea with state aggregation, let's see, is that we have some number of groups that we define that we want to work with. So here, the value is set to 10, and then you need to have some function which assigns the true states to the group they're in. Now, in the case of this random walk, the states are just like integer values. They're just like 1 to 1,000. And it's very easy to do this state aggregation because we're just going to use this, rounding function, where we're just going to take a state, we're going to divide it by the group size, and then round that value off. And what this chart is showing is for all of the states, what this function maps them into this group. So this axis is the group they're assigned to. And here, the number of parameters in the approximation just matches the number of groups. So here there's going to be 10 parameters. Each parameter will represent the value estimate for that group. And then the reason why it's called state aggregation is that all of the states that are in this group will be estimated as having the same value. And this also really simply shows what kind of compression we're doing for this estimation. Whereas for the full problem, we would need 1,000 different estimates. And whereas with state aggregation, we're compressing that into just 10 estimates. So this is a very simple method. The only estimates that affect each other are going to be states that fall within the same group. So you can see if we change the estimate of group 6, for example, you could see that won't affect any of the other groups because it will only affect states in the same group. So yeah, and also in the case of state aggregation, the gradient takes on a particularly simple form, which is that the gradient of a state with respect to the parameters, the value of the gradient is 1 if for the parameter that matches the group index, and it's 0 for everything else. So, it just means that the gradient update will only ever affect one single parameter, and that is the parameter that represents the group that state is in. So does that make sense to people? Are there any questions about how the state aggregation works? And this is also like a one-dimensional problem, like the states are just this value. You could use state aggregation in any type of problem, but the function that assigns a state to a group would then have to be more complicated. But you could use a hashing function, like you could do any number of things. Here it's just there's no overlap but between the groups. And we're just sort of bucketing the state space into these different categories. You see here, if I change this number, you could see it just updates, the number of groups.
I maybe have a quick question
Mm-hmm.
regarding saving the states here and kind of debugging a complicated problem. How would the data structure look like to essentially understand and debug like a really complicated state like this?
Well, here the states are just, in this random walk example, the states are just, integer values. So it's all simple. I mean, it depends on the problem. Like the states could represent anything you want. And yeah, you would have to, you know, like define the data type for the state and then define like the group assignment. And I mean, yeah, you could do that, I guess, improperly. But the important thing is if you have like 10 groups or something, you want the states to be distributed among all the groups. Like you could mistakenly define a function that, assigned all the states to like just one of those groups, and then it wouldn't be very, very useful. But yeah, I don't know. I guess I'm not sure exactly how to answer that because it really would depend on like what the state representation is. We'll see later, like slightly more complicated than this is having states that are numerical values, but just like pairs of them or, triples of them. But usually whatever the state is, eventually you would have to convert it into, a list of numerical values somehow. And then, you could define a group assignment function that operated on vectors of those values. But I guess if you're really not sure, like a simple, like you could always use some kind of hashing function to do this assignment. And even if it's done sort of randomly, you hope that they just end up getting evenly distributed among the groups. Yeah. But yeah, this example isn't, I mean, because the states here are very simple, this example is not going to be able to answer those kind of questions. But yeah, like that could happen in a later example. But for now, the point of this is more to understand with a very simple example how these techniques would work with state aggregation.
Yeah, I wonder if you could just graph all the gradients and then kind of visualize that on a map and then see basically what's going on in terms of the reinforcement learning process.
Uh, yeah, I think maybe some of what you're asking will become is more clear as we move on because here this is just showing how the groups are assigned, but not what happens like during the learning process. But I'll get to that later. But to show how this connects to the setup in the previous section, to do the gradient setup, remember how we need this like parameter update function. So here, the parameter update doesn't even need to compute the gradient. And here the arguments are just the plain arguments that I showed are the only required arguments. So there's the list of parameters, which in this case is going to be one parameter for every group. There's going to be the state, like the current state, the target value, and the step size. And here, we have to define our, group assignment function, which I just showed earlier. It's just this function. This is how it assigns the groups. But this function just needs to operate on whatever the states are. So we assign the state a group. This part doesn't really matter. This is just the catch if there's actually like a problem with the group assignment, if it overshoots the parameter list. But then the like the current target value here, like v hat, which this is related to, right? If you go back to this update rule, so as we can compare this like 9.5, to what this parameter update is doing. So it's computing v hat, which in the case of state aggregation, v hat is just the parameter at the group index. So it's as simple as it could get. It's just this, there's no processing. It's just extracting this value. Then we have the delta here, which is this expression, which is the target value minus the estimate. And then the gradient update here, because in this case, the gradient just has a value of 1 at this index. So the only parameter that gets updated is the one at index I, and it's just the step size times delta. And this also is returning the error term, which isn't part of the update, but that's just to keep track of the error over time. Yeah, so in this case, you could see like we never actually needed to compute this gradient. We have to compute this delta. And that's, we don't have to compute the gradient because most of the gradient updates are just 0. So this doesn't even evaluate the values of 0 and add them. It's only doing the update at the index that matters. The value function is also pretty simple. Again, all it does is take the state, assign it to a group, and then get the parameter value at the group index. And then, once we have the value function and the parameter update, then, we can just pass that along into the, this previously defined function. And then, this sort of run function ends up constructing the parameter list, which in this case is a vector of the length, the number of groups. And then when we run the estimation, it will update these parameters. And then we can define the value estimate using that parameter vector. So this, is the result of doing that process, at least in this case for, let's see how many, I think this ran for, I really run for that long, for 100,000. Okay, that's like quite a few episodes, I guess. Yeah, you can see here, it's running for 100,000 episodes, and it computes these updates. And, you can see how the values are all the same across all the states that lie within the same group. This histogram thing is showing the distribution, which is how often the states were visited. This is the most visited state in the middle because it's the starting state. And then the states on the edge become less frequently visited. And one thing that's noted in the book is that you can see that for the edge groups, that the estimate really is not, is accurate for the edge groups as it is like for this group, because you can see that the values of these states are quite far from the true value, which is represented by this blue line. And, the reason why these estimates are worse after, a certain number of episodes is because the objective, value error is using the state distribution as part of the error. So it's weighting the error of the states in the middle more. They're more important for this error to be low than the states on the edge. So it's just showing like how, there's this compromise where the approximation cares more about the states in the middle than the ones on the edge. So yeah, that is sort of showing at least an example of how this Monte Carlo method works for the random walk example. And the true value here is computed with one of the tabular methods from part 1 of the book. So yeah, it's mostly like a straight line. But yeah, because the reward is 1 at the right edge and -1 at the left edge, you can see how, these values approach each of those reward values as you get closer to the edge. And in the middle, the reward is 0, indicating that there's an equal probability of terminating to the left or to the right when you start in the middle, which is what you'd expect from this random process. So are any questions about this figure 9.1? Or what the approximation looks like? So the next section makes this a little more general. So we talk about linear methods. They have this form where there's a parameter vector, and each value estimate is just the inner product of the parameter vector with some state representation vector. Now, that means that in order to define any linear method, you have to define this function which maps a state to some vector representation of a size d. And then the parameter vector will have size d. So all the linear methods will have this in common. Also, in the case of linear methods, the gradient, if we differentiate each of these with respect to the w, we can see that the gradient is just going to be the feature vector. So it makes the parameter update have this simple form here. This should be replaced by this inner product here. And then, yeah, so here, for setting up a linear method, it is useful, like in this case of state aggregation, we didn't need any additional arguments to this. In the case of the linear method, it's helpful to have this gradient vector, which will match the parameter vector. And what the gradient vector, well, actually, wait, is this gradient vector even? Actually, I guess the way I wrote this doesn't even need to use the gradient vector, because what this does is that it computes v hat. So what it does need is this state representation vector. So this, here we're assuming that the state has already been mapped to the state representation. And then once we have it, we can compute v hat by taking the dot product and then delta. And then here the parameter update will be this full vector update, because in general, depending on the state representation, it's possible that more than one parameter will get updated. And that's what occurs here. This delta is just a single value, but this value will then be broadcast across the state representation values. And in the case of state aggregation, if we were to have done it in this way, the state representation would be a vector that just has a single value in it, where there's just a value of 1 at the representation index. There's also, the reason why there's two things defined here is because if our state representation, if we use a sparse vector, which would be very useful for the case of state aggregation where there's just a single non-zero value, then we don't actually have to go through all the parameter values. We can just go through the ones where this just means that it's only going through the state representation indices that are non-zero in this case. So then in order to set up one of these linear problems, we know that if we have the state representation, we can do all this. But in order to use a linear method, we have to have a way of mapping the state to the state representation. So that's what's provided here. Like if you want to set up one of these linear problems, you need to define what is the state representation. It's going to be some kind of either vector or sparse vector of some size. And then there's some function that updates that vector, and it updates it, it updates the state representation with some given state that you're using. And then, this parameter update, the way it works is it has the required arguments. And then there's this, it turns out actually that this gradient argument isn't necessary, but the state representation is required, and that gets updated with whatever the state is. And then the parameter update can be called, which uses this linear style parameter update. Yeah, so then in order to use one of these methods, you have to actually, the important part about the method is what's called the feature construction, which is how a state is turned into one of these feature vectors. So that is the subject of that. They give, several examples in the book of different features that you could construct. One of the first examples are polynomials, but polynomials are in this class of order feature methods where there is some set of coefficients that goes up to a certain order. And here let me see, I have a function here, which this is the subject of one of the exercises too. So yeah, when you use one of these order methods, you basically define an order that you care about. So, you go up to a certain point, and then you end up constructing these coefficients. So like in this example, let's say you have a state representation where there are two numerical values in the state. And then there is some k value which defines the order that you want to go up to. And in the case of polynomial features, the different features are going to be some integer power that we take of each of the numerical values in the state. So every feature in the feature vector is going to be, some product of the state values to some power. And the powers are what the order feature method determines, and it just iterates through all the powers up to k. So here, this is showing all of the powers up to k equals 2, but this 1 is the case where both powers are 0. So we'd have s1 to the 0 times s2 to the 0, which is just the value of 1. Then we have s1 times s2 to the 0, which is 1, s2 times s1 to the 0, which is 1. And then it goes all the way up to both values being taken to the maximum exponent. But this is just the case in the polynomial case. But in general, there's other order methods where, these values, instead of being exponents, they're used for something else. But in order to use one of these methods, like this is showing in exercise 9.3, it just asks like, when you have n equals 2 and k equals 2, what are all of the order feature like values that you care about? And this is just showing that there's 9 different values. In general, the number of features will be given by this term, which is n plus 1 to the k, where n is the number of values in the state, and k is oh wait, sorry, I'm saying this backwards. K is the number of values in the state. N is the maximum order that we care about. So here, this is showing how when we iterate through all the powers, like this is showing for n equals 2 and k equals 2, all the different combinations of exponents that we care about. But as you change this, like if you went up to 3, then, you would have a additional terms here. But this function here, sorry, you can actually run this, because all these order methods use these coefficients. So if we set like both to 2, right, you end up getting this list of coefficients. And then, if you make this 3, then you get 16 coefficients and 4. So depending on this method, and this is going to match the number of things in the feature vector. Oh, sorry. Asher, you had a question. How do you measure reward? So, sorry, this is sort of covered in the earlier sections, but whenever you define one of these problems, part of the problem setup is that there is a reward given for every step that's taken, and that's part of like the environment is what gives you the reward. So that has to be defined ahead of time. Yeah, like if you don't have a way of assigning the reward, that's not like a well-defined problem. Uh, Sorry, this is like a longer question. In the case of the random walk example, like this is just a toy example used to describe how these methods work, but the only reward values are just when you terminate on either edge of the random walk. But um, in a more complicated problem, the thing that is being maximized is not like the immediate reward, but it's the sum of all future rewards that you would experience. So the goal is to um, basically create a policy that acts in the environment and it would achieve the maximum like long-term reward out to, like forever of interacting with this environment either to the end of an episode or, indefinitely if it's a problem that goes on forever. So that's how these problems are defined is what you're trying to optimize. And yeah, but here in this chapter, since it's introducing um, this new style of function approximation, we're just sticking with the case of computing the values for a set policy. Or in the case of the random walk, there's no policy. It's just trying to compute the value of every state where the rewards are assigned, as I described it. Yeah. So when we do use one of these order methods, we have to define the coefficients and then how those coefficients are translated into the different feature values. So in the case of the polynomial basis, those coefficients are used as exponents in this product expression. And this is just showing in the case of the random walk, the states are just, from 1 to 1,000. And this is showing like in this case, the number of parameters will actually match the order size because k equals 1 in this case. So this is just showing for each order of the polynomial what the value would be at that state. So like for state 800, you would have this feature vector that would be, 5 elements that would be shown by each of these different line values here, depending on how high the order is. Right, and that's just being computed by this expression where we're taking the product of each state value. Also, it's important to note that for all these methods that create these order features, we end up mapping the state into some value between 0 and 1. And that's why these all are sort of bounded in this range. That's commonly done for a lot of these techniques. So it does help if we know the minimum and maximum values ahead of time, because that way we can do this mapping. So showed that. Yeah. So this is showing the way the order feature gradient works, because this is a linear method, right? In order to use, so I already showed for the linear methods, for any linear method, the only thing we have to define is the state representation and how to update it, and then everything else is already taken care of. So for these order features, in order to use one of these techniques, all we have to do is define the function that updates the feature vector, which in the case of the polynomial case is just this, where again we do have to map the value to some value between 0 and 1, which is what the min and max is used here, and then we just take the exponent here because we're in the one-dimensional case. In general, if we have a state which is more than one numerical value, we have to take the product. But we're still taking the product using all these, the E here represents all the order feature coefficients, which here are like these values here. So this is showing, if you use these polynomial feature vectors, in the book, they have an example where they show a graph of like the error over time. So their point is that the thing they introduce next is the Fourier basis, which ends up having, nicer properties for doing function approximation. You could see here like the polynomial basis. I mean, if you look at these feature vectors, there is sort of like a large amount of asymmetry with how these work. And usually you would want to use a different class of polynomials that sort of filled the space better. But you could see some of the structure of the polynomial features coming through in this approximation where this green line is the true value, and this is showing both the Monte Carlo and the TD method, which we're free to use both methods using the polynomial features. This is showing up to order 5 for the polynomial features. If I change this here, like if I make it 10, then that just means there's going to be like 10 parameters instead of 5 parameters in the function approximation. And this is doing it, learning for 5,000 episodes. You also have to define the step size here. And these are all things whenever you use function approximation techniques, you have to, sort of see what happens with different step sizes. You can use some heuristics, like you could see, ideally the error is dropping over time. If I make this step size too large, then this whole process is going to become a lot more unstable. And now you could see this is much further away from the true value estimate. But there isn't necessarily like a great automatic way of picking the step size. Usually it is done heuristically or just by empirical testing. So once we have these coefficients, right, like these coefficients, in the polynomial case, we use them to construct features like this, where we have these products with the exponents. In the Fourier case, in the Fourier basis, there is a very different form which is used. This is showing in 2 dimensions different Fourier features, but Fourier features in the 1-dimensional case, the higher order you go, the more the more maxima and minima there are in the Fourier features, and it sort of it can end up covering finer, more rapid variations across the state space. But this is showing, again, we map all the state values from 0 to 1. And then if once you map a state from 0 to 1, then wherever the state falls here, like the first Fourier feature would be the value on this line, the second Fourier feature would be on this line, the third one here. And you end up building up these feature vectors by selecting the values from these different cosine functions, where the what is it called? But the frequency of the functions increases as the features go up. So these functions do a better job of like more symmetrically filling the state space. And here, again, all we have to do is sort of pass in, this is just another order feature method. So once we define how the order features are calculated, then we can use all the previously defined techniques. You can just do the approximation again, and you can see how this is a lot more forgiving, at least, I mean, in the TD case, it's getting quite close to the true value here, which is reflected in this chart is just sort of showing, like in general, the Fourier, it doesn't matter too much when we increase the order. Like here, this is using order, here, I mean, I guess it was set on order 10. As you change the order of the Fourier features, like if I make this 100, like now you could see it has the ability to do a lot more fine variation, but it's also much noisier. Probably the step size has to be, adjusted to a smaller value, but if you make it too small, then you can see the values at the edge are taking a lot longer to converge. And that also is reflecting the fact that the values on the edge are visited far less frequently than the values in the middle. So, but the Fourier approximation does a very good job even at a very low order of just 5. So you see, in general, much smoother. Yeah, let me see your question. Is it wise to? I'm sorry, I'm not, Asher. I'm not sure exactly what you mean by that. I mean here, like the state. Do you mean like? So we're sort of in general, we're going to be given like the state space in this random walk example. It just happens to be very simple, where they're just you know a single numerical value. But uh, yeah, and then we're sort of mapping it into this. Like if we have Fourier features of order five, like yeah, like the sort of state representation we're mapping it into are these, like we just have five parameters that we're using to approximate the values of a whole, a state of 1,000. So I guess like the better the method, the more approximation power it would have with fewer parameters. So like ideally we would like that's why like with the Fourier method, even with an order of just five, it's very good at approximating this entire like across this entire state space. Whereas in the case of polynomial features, like even if we increase this a lot, it might have a hard time approximate like generalizing across all these states. But these methods are very different from like the state aggregation methods, where we can sort of increase the number of states and make these buckets smaller. And the nice thing about these methods is that if something goes wrong, like in this part of the approximation, it won't necessarily affect these other buckets. Whereas for these features, the way these features work and why you see this sort of wavy behavior across the whole state space, here, like as we change parameters, it will in general affect all of the states in the approximation. So, there's pluses and minuses to all the techniques. But here, because this chapter goes through a lot of these different linear feature construction options, I'm just going to try to get to a few more of them. So coarse coding is the next one. In coarse coding, it's sort of similar to state aggregation in that we cover the state space with some set of buckets, except the difference is that now the buckets can overlap somehow. And here, like the size, like the number of features will be sort of in general the number of these buckets. And then the feature vector would be just these one hot vectors where there's a value of one representing, which buckets a state is in. So it's very similar to state aggregation. It's just that now there's going to be more than one feature that's activated. So this is showing an example in the one-dimensional case where, we have this state space, and then each of these lines is one of the buckets. And then this vertical line would represent what state we care about. And the lines that this black line intersects would be the activated states. So this is showing, like in this case, what would the feature vector be as we move this around. So you could just see like in one of these states on the right here, these right two features are activated. Whereas if we move over to the left side, only this one feature is activated. So this is what's called, a type of coarse coding. And here it's easy to show it in the one-dimensional case. In a higher dimensional case, it's much harder to figure out how you define these regions. But that is where tile coding comes in. So tile coding is a systematic way to do coarse coding, where we define a number of tilings. The tiling is defined by defining a tile size, and then we're going to just repeat the tile across the state space. And then we're going to shift that entire tiling by some offset vector. This is showing an offset vector, which is just, 1 and 1. So it's the symmetric offset. The offset's the same in both directions. And then we can do a number of different offsets. And then when we figure out what the feature vector is for a state, there is going to be, a value of 1 for each, for whichever tile a state is in. So this blue tiling is showing like the first tiling. And you can see that whatever state we pick, that state is in one of these tiles, right, for tiling 1. And that is going to be true for all of the tiling. So for tiling 2, it will be in a particular tile for that tiling. And in this case, the number of features, like the state representation size, will be the number of tiles for a single tiling times the number of tilings, because it's going to end up being this long vector. But the number of active features is always like only going to be, like in this case, if there's 4 tilings, there's just going to be 4 active features out of all the different tilings there are. So here they show a case where you have like, 16 tiles per tiling and then 4 tilings. So overall there's 64 components to the feature vector, and 4 of them will be non-zero for a given activation. Yeah, it's easier in the one-dimensional case, because in the one-dimensional case, well, here, I'll just show an example here where this is showing, if we define a tiling for the random walk example, this is showing for each state what the feature vectors are. So here, because there's just 2 tilings, there's only 2 active features, depending on what state we're in. And the tile size here is going to affect how many tiles there are total in one of these things that covers the state space. So if I like lower this down, you can see it ends up just making more finer steps in the representation, but the number of active features is always controlled by the number of tilings. So here, like as the number of tilings goes up, you have more active features, but these feature vectors are always these one-hot vectors, which is why they're most naturally represented by a sparse vector, because there's just values of 1, and otherwise, yeah. So I know, like, unless you sort of write it and look at it more closely, it's a little hard to tell what's happening with the tiling, but the point is that it just converts the state into this sort of sparse representation. So they show an example here where tile coding. So, oh yeah, also, if you have a single tiling, like if you go back up here and change this to 1 tiling, right? This looks like the state aggregation case where, right, we just have these states are grouped. And then the power of this technique comes when we add more tilings, because we end up having, finer gradation. So here, this is showing example. If you zoom in on these, you can see that ultimately it's still like creating these steps, but the steps available in the approximation get much finer as we increase the number of tilings. So really, like, the number of tilings is more important than the size of each tile. I mean, in terms of what gives it more approximation power. But yeah, you can see here also, it seems like the TD method here does a little better job of handling the edge states. But again, this is also a matter of selecting the step size parameter. Yeah, and this is again going for 5,000 episodes, just like the previous example. Yeah, and again, this is also like, it's still a linear method. We do need to know, like, the tile coding setup will end up, once we give it the tile size, the number of tilings, and what kind of displacement we want, which is how the tilings are shifted, then we know from that the number of parameters, and then the parameter update. I think I wrote, Yeah, I think this is just using, well, this should be using like the same linear method code as before, because yeah, all we need to do is define the feature vector update. Yeah, so this is using, yeah, like the feature vector update is just, yeah, uses this thing which ends up taking the whole tiling setup and figuring out, which tile the state is in for each tiling. But yeah, in general, I mean, this is one implementation, but in the book they mention they have some other implementation code that they use. You could also use like different shape tilings, but this is just doing um, the way this is written. All the tiles are going to be rectangles of some sort rather than these odd shapes. Yeah. Um, yeah. The other point brought up in tile coding is that like the shape of the tiles kind of affect um, how the generalization works. So this exercise sort of asking, suppose that, we have a two-dimensional state space like this, but one of the dimensions is much more likely to have an effect on the value than the other. So generalization should be across the dimension rather than along it. So they're saying that as you move across the state space, like in this direction, the value changes very rapidly. Whereas once this part of the state is defined, moving up and down here would not affect the state value that much. So if you create tiles that have this elongated shape like this, where there's many more tiles in one direction than another, it means that the approximation is freer to update the value more rapidly in this direction than in the other direction. Like there's more, finer, like there's the ability to change the value more quickly and with more detail. So you would sort of use these asymmetrical tile shapes if you had a problem. And that's a case of sort of if you have knowledge of the environment, like some, information about the problem, you can sort of inject that information into the tiling shape setup. Let me see this. These exercises, I don't think matter as much to talk about. Here, I'll move. So the book also mentions a few other techniques it mentions, but doesn't provide any sort of implementation of. But one of the things they mention, which is of probably a lot more interest today, is the nonlinear function approximation, which uses neural networks. So I had the last time I went through this, I didn't actually implement anything like this, but this time, using the sort of gradient and TD0 function setup I have, I can use this. There's this package. I have this sort of totally unrelated to reinforcement learning, but this it's not actually shown here, but I'm using this package, which you can see in the dependencies of in this GitHub repository. But this is a very simple like package for doing these like fully connected neural nets. And all you have to do to use it is define like the layer size and the number of layers. So this is showing an approximation where like, the neural network is just defined by this vector, and it's assuming there's like a tanh activation function being used and a squared, it's also using like the squared error, but this gradient update for the neural network, there's all these other, the reason why there's all these other placeholder arguments here is because this like cost function calculation, which it's using the squared error for the cost function, it needs to update all these other like intermediate memory structures, which are storing the gradients, the activations, a bunch of stuff. But once you compute all this, the parameter update can be done yeah, once the gradients are computed. But again, these gradients that the neural network is computing, the reason why I like the cost functions here is that like the gradient, it's computing the gradient of the parameters with respect to the cost function, not just the gradient like earlier in the book. This is why I mentioned how earlier in the book, writing the update like this, you know, where you compute the gradient of the value estimate, and then this is a separate term. Like most neural network packages will end up like you'll tell it what the cost function is, and then, you know, this entire update will be computed as a separate function. And that's what's being done here. So yeah, that's why these parameter updates. But again, also in order to use this technique, you do have to have a way of taking a state and like mapping it into a feature vector. So that part is the same as with the linear methods. But now the feature vector, like in the case of the state aggregation, I mean, I'm sorry, not in the case. In the case of the random walk, like instead of defining our own features, we will just take a state and put it, you know, we'll map it to like a range that in this case, it'll be like mean 0, variance 1, try to make the learning nicer. But then, you know, the neural network will handle all the other, you know, potential feature vectors. Like in this case, because the layer size is only 2, there are very few parameters here. So this is showing like this is what the parameters look like of this network. There's like biases and gradients, but you know, there aren't that many parameters here. This is for like 2 layers and 2 neurons per layer. But this is an example of the approximation it found with this size network. Again, this is also very sensitive to like how you select the learning rate, how you do the parameter update. And usually when you use one of these neural network techniques, like here, this parameter update is like computing the gradients, and then it's just updating the parameters with the gradients and some learning rate, alpha. But you know, usually when you use a neural network like this, you want to do some sort of more elaborate parameter update where there's like a separate learning rate for each parameter. And that can be done here, but you know, it would require like writing an additional function. And probably to get this technique to work really well, you would have to, you know, do some more elaborate parameter update to make the process more stable. You can see like it's doing a decent enough job, especially I think the TD method. I mean, you could see like the strength of this is it has a lot of approximation power. Like it can sort of make whatever functional shape you want, but especially in like the semi-gradient method, you lose a lot of guarantees that you had from the linear method. And, you know, you'd think like you have more approximation power. Like if I make this, you know, each layer like size 20 or something, this is going to have a lot more approximation power. Like this still looks okay, but then, you know, you have to make sure that you adjust the learning rate to match. Probably the learning rate would have to be much smaller as you increase the parameter size. And also it's possible that you can always make the network more complicated with more parameters, but then this number of episodes that is training over might also be inadequate. Like you may need more training data for this to work. Now, in the case, like unlike traditional like machine learning techniques, here, like there's no set data set that we're learning on. The data is always being generated by the environment. And in the case of Monte Carlo learning, the target, you know, is always like the target we're getting from sampling from the environment. So you usually don't, I mean, there's like overtraining would be like if the model is overfit to the data, which would be different from having like, if I make the learning rate like too large, then the learning process just won't converge very well. It'll be bouncing around too much. And that's a case of just like this here, the learning rate is way too high. But usually if we give the network more like more powerful approximating power, you know, we're sort of, yes, we are overtraining on this particular environment. So you wouldn't expect this to transfer to a different environment. But, that's sort of a separate topic. Like, because also like we don't have to worry as much about overfitting because we can always generate, like we sort of have an infinite amount of data at our disposal. Like if I increase the number of training steps here, I'm not retraining over the same set of data every time it runs an episode. It is going to be, having an entirely unique set of training examples for that. So yeah, that's, I mean, usually why you don't worry about the overfitting case is because the actual data set is being added to as you run it for more episodes. But yeah, I mean, those questions are more, they will come up in other chapters. Like this example is very simple, and also like there's no danger of overfitting in this case because we're only concerned with the performance on this random walk example. Okay, I mean, the remainder of the chapter is, it does some stuff with elaborating more on how temporal difference learning works, but I don't know if we should go over that now. I mean, some of the exercises, yeah. I mean, I guess the remainder of the last few sections of the chapter don't really fit into this framework of what I've shown so far with using the semi-gradient and the gradient Monte Carlo estimation. So maybe we'll save it for next time, because there's also this discussion of these non-parametric techniques and these kernel techniques, which is pretty interesting. And I did actually create an implementation of these methods, but I think it might be a little too different. It might be a little confusing to discuss it now, because yeah, they're probably worth spending a little more time on. I'm trying to think. And in terms of the exercises, yeah, these, if you want to like see the exercise answers, you can always like look at these notes and look at them. I don't think these set up, like we already went through 1 and 3 last time, and then 4, 5, and 6. I don't think are that important. Yeah, and I think exercises 7 and 8 are worth looking at, but might be, yeah, but are probably worth saving for next time. So yeah, I mean, it basically covered the linear and nonlinear methods using gradient and semi-gradient techniques. Yeah, so maybe we can cover just the last little bit of chapter 9 next time, and then move on to chapter 10, which is actually about finding the optimal policy, which we have not covered at all in this chapter, because this chapter is only concerned with approximating the value function with different techniques.